Hello everyone, we're Team Buet WaveX from Bangladesh University of Engineering and Technology, Buet, and we're pleased to present our Phase 2 video submission for the IEEE 2026 Signal Processing Cup on real-time audio-visual zooming on smartphones. Our team is supervised by Dr. M.D. Kamrul Hassan, professor in the Faculty of Electrical and Electronic Engineering at Buet, whose expertise in signal processing and communication systems has guided the overall technical direction of this work. We're also fortunate to have M.D. Jainalam as our tutor, who is currently a doctoral student in Electrical and Computer Engineering at Johns Hopkins University. His research background in advanced signal processing and learning-based methods has provided valuable technical insight throughout the project. The undergraduate members of Team Buet WaveX are as follows: MD Tamim Shorkar, MD Tahir Hassan, MD Tahmid Hassan, MD Abrar Fayaz, Zarif Shahriar Ahmed, and Noor Razin. Together, we worked collaboratively on system design, MATLAB simulation, performance evaluation, and edge-focused implementation aspects. In the following sections, we will present our proposed methodology, implementation details, and quantitative results for both anechoic and reverberant environments.
I'm Razin, and I'm going to walk you through the whole pipeline of our audio zoom project. So we start by taking a video input, and then we extract the first frame. And in that first frame, we select a region of interest. Region of interest defines which person will focus on while zooming the audio. So in this photo, there are two persons, but as the male is more centered in this image, so the male would be our desired target. We calculate this through various techniques. We use media by pose estimation, cascade face detection for left and right profiles, and also front of face and upper body detection. If there are two people in one photo, two persons in one photo, then we will prioritize the center placed person. For that, we use weighted averages. So we get one input frame, then we run all 5 detectors, and then we take weighted average and take the highest score among those, and thus we find a region of interest. These are more examples of that. After we find a region of interest, then we have to figure out what is the gender of this person. For that, we use a gender classification model. We used a custom trained MobileNet V3 small model on the UTK face database, which contains almost 24,000 files. Then, when we know that what is the gender of our person of interest, we select the audio model. We've trained two audio models for this, male model and female model, and we use this separate model for separate genders. Then we chunk the audio in 3-second portions. Why? Because our model was trained on 3-second audios. The model will perform best if the audio length is 3 seconds. So if we get a long audio, we divide it in 3 seconds, and then we perform inference. So basically, we separate the male or separate the female voices. And then after the separations are done, then we again add them back together and stitch to a final output. We also use smoothing in the edges of the audio file, so there isn't harsh click heard. Then this stitch output is run through deep filter net and some post-processing techniques, and thus we finally achieve our post-processed output. Then we have a separated audio. We know what our target is, and then the last part is how we sync it with the zoom. For this, we've thought of some techniques which we will implement in the next phase of the competition. Now let's walk you through some examples. So this is the code of our full pipeline, which basically runs inference and then chunks the audios and runs it through the models. We also have a male and female model, separate models, gender classification. Basically what I explained in the presentation. So we're gonna run it in a video and produce the outputs in real time. Here we've generated the region of interest, the extracted audio from the video file, and the separated target.
The trouble has been that the people were all asleep while I was there in the early morning expending. The trouble has been that the people were all asleep while I was there in the early. The man was surely Henson of Olympia.
And after that, we can run our post-process module and basically produce a final result. Thank you.
As you can see, our sampling frequency is 16,000, sound duration is 3 seconds. We choose our SNR as a variable, so it's between 5 to 10 decibel. Rest per target is also 5. That means each target will have 5 different interference file. And then we have some sourcing probabilities for noise and music. P noise, P music, probability of noise getting added, and same for music. And there are weights for mixing in the interference file data actually. So, and then we have our microphone position here and our target position, interference position. These are actually generated by these two functions. So our target in the extraction has this very small jitter, and in the y direction it's actually 0.5 meter to 1.5 meter from their center rather than 1. So we are actually basically generalizing all these things here. And interference is also a variable. It's anywhere in the room, but it is always at a distance minimum of 0.5 meter from the walls. And then we have our room impulse response generation function. Here you can see when RT60 is 0, it's just a delay and distance based attenuation for each microphone. And for the reverberant case, we compute reflections here and compute reflections up to maximum order based on the wall absorption coefficient derived from the RT60 values, which is 0.5 for this case obviously when reverberation exists. And then we have all our directories here and segmented male audio, female audio, noise and music. All these files have 3-second noise, music, male, female audios here, and number of files to process 10 in this example. And then our interference file is being generated. So when our target is male, in interference we have female, noise and music. Female in this case will always get included, and noise and music will be inserted via this condition. So, and if the target is female, then interference will have male obviously plus noise plus music. This will make our data more generalized. And then we have our room impulse response functions being called. Then we are convolving with them with our clean target and clean interference. Then scaling is applied so that we get a SIR of 0 dB. White Gaussian noise is added, so SNR is between 5 dB to 10 dB. Our mixture is then generalized here. Then we are calculating some metrics, storing all this data in CSV format, also in MET format. So yeah, that's pretty much it. And if we want to have a look at our data, so if we load this in the metadata, we can see all those things. As you can see that in example ID 1, 2, 3, 4 to up to 10, and there is a single target file names, and for this single target file name we have 5 different interference file name, and including RT60 value 0 and 0.5. so basically each target file will give us 10 metadata here. Then we also can see our SIR, SNR, frequency, scale factor, obviously normalization factor, all those things here. And yeah, and we can see our targets, interference, mixture, all are basically 3-second audio files, dual channel. So first, in the Muson file, pitch are categorized into male. Here all files only have male audios and female audios. Same goes for music and noise. These are already categorized before. And then we segmented all this into 3-second audios, and these files are in my MATLAB directory, as you can see here. Here you can see our segmented male audio, female audio, music and noise, so all those things here. This is our computation specific data generation, our initial approach. So our fixed parameters here, all those things. Sound duration is 3-second, room size, SIR 0 dB, SNR 5 dB, RT60 values, and our fixed microphone array, our source positions, all those things. Here in this example, our target is male, so male speech segmented male audio target directory. Interface is female. This is our room impulse response generation function, event source method. In case of RT60 is equals to 0, this is anechoic condition, direct path only, no reflection. When in reverberant condition, event source method with reflections is applied. Our room impulse response functions are being called here. They are being convolved with clean target, clean interference. Scaling is applied to achieve SIR of 0 dB. We are adding white Gaussian noise to make SNR 5 dB, normalizing all those things, calculating some metrics, storing all those things as CSV format and also as a MAT format. So yeah, this is pretty much it. Then initially as pre-processing we tried MVDR, minimum variance distortionless response. So you can see here in this we are implementing simple MVDR. So then, but if I run this, as you can see the improvement is not so good. So it's not great for small distance, in this case 8 centimeters microphone distance and only 2 microphone arrays. So then we also did some frequency dependent beamforming. As you can see, there is not much difference here. Also you can see the angles, the nulling, all those things. Chose to have multiple beamforming options here, and this is our function. We are giving a 2-channel mixed in as an input, and as output we will get mic 1, mic 2. This is what we give here, and we'll get delay and sum, STR2 for target which is 90 degree, null steering, null at 40 degrees, so interference is getting nulled, and differential beamforming also. All those things are applied here. Our STFT parameters, we are using Hanning window, so creating spectrograms, calculating the phase of target and interference. So steering vector can be calculated here by this logic. We are also applying LCMB, null steering beamforming, so differential beamforming. We are doing now inverse STFT to transform all those things into time domain, normalizing and saving the outputs. Then if I run one thing here, so as you can see now we have 5 channels, mic 1, mic 2, and if we want to listen like differential beamforming, so here you can see this is only the interference here. If we suppose mic 2, this is the total mixed file. So the next task we did was we applied these beamformings in our model DPRN and TASNet. So this is for our beamforming. This is our model trained without any beamforming as pre-processing. So you can see the SISGR improvement, all those things, around 12 dB, and this is with beamforming, so 5 channels. So there is no significant change in SISGR. We also calculated PSQ and STY for 2 channel. This is without beamforming, and 5 channel this is with beamforming, and you can see the improvement is not that significant. So then we came to realization that our beamforming method do not add any significant improvement, and we then chose to update our dataset generation, so generalize things.
Hello everyone, I'm Abrar and I will walk you through the modeling and training strategy we have developed for phase 2. To solve the audio-visual zoom challenge, we needed an architecture that strictly balances high-fidelity source separation with the ability to model long-term dependencies in audio. We made a deliberate choice to move away from the traditional frequency domain masking, which often struggles with phase, and instead implemented a fully time domain approach, the DPRN testnet. We designed this model with 3 specific goals in our mind. First, it is end-to-end time domain. This allows us to avoid heavy spectral post-processing and work directly with the waveform. Second, it excels at long-range context modeling because effective speech separation relies on consistency over time. The dual-path design captures the full temporal structure of the conversation. And finally, the stability. It is practical to evaluate on short segments and ensuring our training remains stable and efficient even with limited compute. Let's start with the dataset we have created. So each training sample is as a .mat file, and for each room condition we load RT mic 1 mix and RT mic 2 mix. These are our 2 input microphone challenge, and these are the mix signal recorded at 2 microphones in the room. These represent what the mic actually captured in a realistic room scenario with target speech plus interference and sometimes reverberation. The prefixes like RT0 and RT05P refers to different room conditions or reverberation times in the dataset. For the target signal, we handle it in a robust way. If the dataset provides a direct target channel like RT mic 1 target, we use that. Otherwise, we generate a clean proxy using clean equals to mic 1 minus a mic 1 interference. We define the sampling rate fs as 16,000 samples per second, as that's a common rate for speech processing, giving us good balance between audio quality and computational cost. Then we set the seg length to be 3 times the sampling rate, meaning each audio segment we work with will be 3 seconds long. This helps us standardize the input length of our model. We also set the number training cycle to 100, indicating it will iterate over our training data 100 times so that our model can effectively learn the pattern from the audio. To prepare audio for our analysis, we define some parameter for the short-term Fourier transform. NFFT is set to 512, which determines the size of frequency analysis window and ultimately how finely we can revolve the frequency content. We set the hop length to 128. This controls how far we slide the analysis window each time. And we use a window size of 512 samples with a hand window created, which smooths the audio created segments to reduce artifacts when we perform transform. This kind of windowing and FFT setup produces spectrogram representations that captures both time and frequency information of the audio, which is essential for many deep learning audio tasks. Finally, we defined a list label RTS containing RT0 and RT05P. And to ensure our model generalizes across acoustic settings for training, we randomly choose RT0 or RT0.5 per sample instead of training separate model. That forces the network to learn a shared representation that works under both reverberation and non-reverberation. This helper function makes sure our audio data is in a standard floating point format that our model and signal processing tool expect. First, it squeezes the input array to remove any unnecessary dimension using np.squeeze, which simplifies array shapes by eliminating excess of length 1. Then it checks if the data is stored as integers, which raw audio often is, and if so, it converts it to float 32 and normalize it by dividing the maximum integer value. This scales the audio into a floating point range that is easier and more stable. The first function ensures every audio clip is exactly the right length. If input array is longer than the desired length, it randomly selects a segment of the right size from somewhere in the waveform. If it's shorter, it pads the end with 0 so the audio reaches its required length. The second function takes a floating point waveform and turns it into a standard 16-bit PCM wave file. This approach produces a proper uncompressed wave file so that it can be played back in standard audio software to work with. This function computes a commonly used objective metric in speech enhancement and source separation called scale invariant signal to distortion ratio, or SISDR. SISDR measures how closely an estimated signal matches a clean reference by comparing the energy of the aligned target component with the energy of the distortion, that is, everything that isn't a true signal. What makes SISDR special is it's scale invariant, meaning difference in overall amplitude doesn't affect the score, which makes the more reliable measure than traditional SDR for evaluating neural modes. Higher SISDR values indicates better reconstruction quality. This function computes the frequency domain loss between a model estimated waveform and the clean target waveform, focusing on the spectrogram magnitudes. In practice, this type of magnitude spectrum loss encourages the model to replicate the spectral structure of the clean audio, and it is commonly used in speech enhancement and speech separation tasks to improve perceptual quality and spectral fidelity. It directly measures how close the predicted spectrum magnitudes are to the reference spectrum magnitudes. Lower value means estimated audio spectral shape better matches the clean audio spectrum. The code defines a helper function that takes a list of file paths and randomly divides them into 3 subsets for training, validation, and testing. First, it creates a random number generator with a fixed seed so the shuffling is reproducible. Then it shuffles the indices of all files randomly, which ensures the data in each split is mixed rather than ordered. After shuffling, it calculates how many examples should go into each subset. Roughly 80% is for the training, 10% is for the validation, and the remaining 10% is for the testing. The training set is to teach the model pattern in the data, and the validation set is used during development to tune the hyperparameter and check for overfitting. And the test set, which the model hasn't seen yet, gives an unbiased evaluation of the final performance. We define several PyTorch data loader objects that warp our dataset splits and feed data into training and evaluation loops. We also create separate validation and test loaders for each reverberant condition, one set for RT0 and one set for RT0.5. By having distinct loaders, we can evaluate performance per condition. This lets us see how well the model generalizes, not just overall, but specifically on dry versus reverberant acoustics. This shows a custom normalization layer called global layer normalization. The goal here is to stabilize training by keeping feature scales consistent. This layer keeps activations well behaved and makes optimization more stable, especially in audio models where amplitude ranges can vary a lot. This function takes a batch of 1D sequences and split them into fixed length overlapping chunks for later processing. The key is unfold. It creates a sliding window view that signal with window length k and hop p, so we get a stack of overlapping frames. We permute dimensions into a convenient layout and return the segmented tensor, along with how much padding we added and the original length. This is a DPRNN block, a key unit in a dual path RNN. It learns context at two scales, within each chunk and across chunks. We use two LSTMs. The intra-RNN runs along the chunk length k to capture the local structure. Then we project back to n and add it with a residual connection. Next, the inter-RNN run across the number of chunks s to capture long-range context, again followed by a projection, layer norm, and a residual add. So each block alternates local and global sequence modeling while keeping training stable. This slide shows our main model, DPRNN testnet, which follows the testnet idea: encode, separate, and then decode. A 1D conf encoder turns the 2 mic waveform into features. Then we normalize and bottleneck them, then split them into overlapping chunks. A stack of DPRNN block models local and long-range context. Then we overlap, add back to full length, and then predict a mask and apply it to the encoded features. And then a transformed conf decoder reconstruct the enhanced waveform. This is our validation loop. We set alpha equals to 0.05 as the weight for the magnitude L1 term is in a hybrid objective. The eval val function runs in evaluation mode with no grad, so it's fast and doesn't store any gradients. We compute two things: the mag L1 loss in SFFT magnitude domain and the SISDR of the model output against the clean reference. We also compute a baseline SISDR using a simple mono mix, just averaging the two microphones. So we can compare the model against a naive input. This is the full training loop. We iterate over epochs, and for batch we move the 2 mic mixture and clean target to the device and clear the optimized state. Here we compute a hybrid loss. The main term is negative SISDR, so maximizing SISDR plus a small magnitude STFT L1 term weighted by alpha to increase spectral fidelity. Then we backpropagate using gradient scalar, unscale, and clip gradients to keep training stable and the step optimizer. After the epochs, we evaluate on both RT0 and RT0.5 validations loader and update the learning rate scheduler based on validation SISDR. We log everything to a history CSV, and whenever the validation SISDR is the best so far, we save a checkpoint. At the end, we reload the best checkpoint and switch the model for final testing. During training, we can see some steady improvement. Validation SISDR increases consistently from 5.3 decibel in the first epoch to above 10 decibel, while the SISDR improvement over the mixture baseline grows from roughly 7 decibel over 12 decibel. The learning rate scheduler gradually decreases the learning rate at performance plateaus, helping the model converge more smoothly in later epochs. On the final test set, the model achieves an average SISDR of about 10.75 decibel with an average improvement of 12.3 decibel over the raw mixture. That means the model is not just slightly better than the input mixture, it significantly suppresses the interference and enhances the target signals. The consistent gap between baseline and model performance confirms that the DPRNN testnet architecture generalizes well across both for reverberant and non-reverberant acoustic condition. This figure shows a qualitative comparison in the non-reverberant condition, and on the left there is a clean reference spectrogram, and on the right there is the model enhanced output. We can see that the main harmonic structure and the low frequency energy bands in the clean signals are also clearly present in the model output. The model preserves the important speech or target components rather than distorting them. At the same time, the background noise floor looks reduced and the spectral pattern appears sharper, which indicates that the network is successfully suppressing interference while keeping the target intact. This figure shows the same qualitative comparison but now under the reverberant condition. In this case, reverberation introduces more temporal smearing. so the energy is spread out and the spectral pattern becomes less sharp compared to the dry condition. Even with that complexity, the model is still able to recover the main low-frequency harmonic structure and preserve the important target components. The output spectrum remains very similar to the clean reference, while some of the diffuse background energy caused by reverberation is reduced.
For this problem set, we choose to implement deep filter net specifically in the post-processing stage. We found that applying it as a preprocessor interfered with our main separation model's ability to distinguish between sources. By using it at the end, we ensure the separation is clean before we refine the audio quality. Deep filter net utilizes a unique two-stage architecture, the ERB envelope stage, which acts like a psychoacoustic equalizer, and the deep filtering stage. Key optimization here is frequency splitting. Before 5 kHz, the model uses deep filtering. This is computationally heavier but essential for restoring the periodic components of human speech. Above 5 kHz, the model uses the ERB stage to enhance the spectral envelope. This mimics human hearing and keeps the real-time factor very lower. For ERB stage, let's look at the math. Our input is x of n, the separated male speech but still noisy speech signal. We first perform a short-time Fourier transformation which generates 481 bins. To achieve high real-time factor, we don't process all 481 bins directly. Instead, we use equivalent rectangular bandwidth to logarithmically compress this into 32 ERB bands based on human perception. The neural network then predicts a real valued gain for each band. By performing pointwise multiplication between these gains and our original signal, we effectively suppress background noise and enhance the spectral envelope. For the frequencies below 5 kHz, we use the deep filtering stage. Here, multi-frame approach is followed after STFT so that we get the multi-frame data which is complex value spectrogram bins. These are fed into DF decoder, a small neural network that predicts a set of complex filter coefficients based on a specific tap number. As the coefficients of the filter is complex valued, they shift the phase of the noisy signal with the predicted clean speech in the complex plane. Frequency restriction is used for optimization in this stage, where the lowest 96 frequency bins are then selected as human audible range, which is 4.8 kHz to 5 kHz. Finally, the output from both steps are concatenated. This gives a final output that is not only noise-free but sounds natural and periodic, all while maintaining a real-time factor of 0.19. We are looking at the spectrogram comparison for 3 stages of our pipeline: the raw microphone signal, the initial separation model's output, and the result after deep filter net processing. We have evaluated this across 2 environments: a dry room with an RT60 of 0 second and a more reverberant space at 0.5 second. To quantify our results, we utilize DNS-MOS, a non-intrusive objective measure that is widely recognized as the gold standard for evaluating perceived audio quality. Our goal was to further enhance the audio after deep filter net. To achieve this, we benchmarked several post-processing techniques against the DNS-MOS scale for both RT60 scenarios. Based on our DNS-MOS result, the moving average technique emerged as the top performer when applied after deep filter net. We can see the final spectrogram here. The moving average effectively smooths out residual artifacts while maintaining the integrity of the speech signal. When comparing our final output to the raw microphone input, which is mixed, we achieved an overall DNS-MOS score of 4.3. To put that in perspective, this places our audio quality squarely between broadcast and studio standards. Finally, we have the comprehensive performance breakdown. This compares our system against the baseline using several key matrices: DNS-MOS for perceived quality, PSQ for speech quality, STOI for integratability, and SNR for noise reduction. Each metric is presented alongside its respective baseline value to highlight the significant performance gains achieved by our model. Finally, we have a side-by-side comparison for both RT60 conditions, demonstrating our model's consistent performance across defined acoustic environment.
One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without. One may walk perhaps 2 or 3 blocks without.